For 70 years, classical computing has been the invisible engine of modern life, humming beneath every email, spreadsheet and streamed film. Machines, once the size of rooms, now sit smugly in our pockets, constantly reminding us just how far we've come. Of course, it hasn't stopped there. Those same foundations now power the algorithms that recommend our next purchase or the systems that guide planes across continents. Even artificial intelligence solutions that have subsequently taken the world by storm. But beneath the marvel lies the same binary mechanics. And as we push those calculations further, faster and smaller, physics at its most atomic scale is beginning to protest, with the neat certainty of ones and zeros beginning to blur. So, science asked, what if we stopped following the rules of classical physics and instead embraced the laws of quantum and qubits? Now, unlike a classical bit trapped in one of two states, a qubit can glide into superposition, a spectrum somewhere in between that crudely represents a dimmer switch for lighting. And when entangled with others, it helps form connections that can steer us towards answering complex problems much faster than classical computing ever could. Of course, there is a catch. To use a qubit, we must measure it, in which requires collapsing it back down into 0 and 1. So the art therefore lies in dancing right up until that collapse and exploiting superposition and entanglement to extract something useful. Think of it this way. A classical computer explores problems much like a detective would, one lead at a time. But quantum pursues many leads simultaneously, reducing cases that might take centuries into resolutions achieved in hours. Take chemistry, for example. Now, designing a new drug means simulating how molecules interact, a task that has continually stretched even the largest supercomputers. But again, with quantum, we can model those interactions directly, potentially opening doors to medicines we haven't yet imagined. We are, of course, still very much at the prototype stage. Quantum is fragile, it's noisy and temperamental. That's why researchers are inventing quantum error correction, clever schemes that employ many imperfect qubits to protect a single reliable one. But of course, that's only part of the challenge. Systems must be cooled, shielded from the faintest of vibrations and isolated from stray electromagnetic noise. And even then, maintaining coherence, the delicate balance that keeps the qubits in superposition, is still a constant battle. But progress is undeniable. Each year, engineers extend coherence times, they refine control methods and scale the number of qubits. And tech giants experiment with different architectures and exotic topological designs, each promising greater stability. And although it's a messy frontier, that's what makes it exciting. Just as early classical computers filled entire rooms, quantum one day will evolve from fragile prototypes into robust tools. And when they do, the breakthroughs won't just be faster calculations, there'll be new ways of seeing problems, new strategies for discovery, and new industries built on possibility rather than certainty.